to hit those as quickly as I can. First, I want to find out if any of you are taking a first mini-term course. You are. Did you know student course evaluations were open? Okay, yeah. They made it sound like students have been notified as if it's a long time ago. I think they just came out. So a couple of days left in the first mini-term, they are out. So if you know of anyone who's taking a mini-term course, tell them the student course evaluations are there, and it really irritates me now. By the way, none of your students have responded yet. Well, if they sent them out last night, that's not surprising, because this was at 9:21. No, this was at 9:21 last night. So I bet you it wasn't too long before that they sent them out, was it? Yeah. Huh?
I guess.
Yeah. So, what a pain. Okay. Anyway, they're out there. Please do the student course evaluations. Which then leads to the next observation, that we're getting awfully close to midterm. And midterm is when they usually ask us to do midterm progress reports. And right now, for a midterm progress report, I have uno, score that I could report. All the rest of you will be failing miserably. Okay, no. Please get something into me this week or next. That could be the research paper. It could be your first test. But try to get something into me this week or next. They usually ask for those midterm progress reports sometime within a week after the midterm. And the midterm is something like next Wednesday or something like that. So try to get me something by then. Okay. Now, a little bit more on a personal note, because I had a long Friday last Friday, and I was only supposed to work 4 hours. I usually don't keep up with them that much, but my wife said, we're going out of town. So we're going out of town. So I'm not going to be on campus day after tomorrow. Birmingham campus, not going to be there this Friday. Okay? Now, next week is a weird week for me. It won't bother this class any unless you happen to be looking for me sometime during the week other than class day, because my Mondays and Wednesdays are fine. But my Tuesday of next week, I have a doctor's appointment that's going to take me, I'll have to leave campus by 9 and probably won't get back until somewhere close to 12 probably. Hopefully, I'll be back by 12. Okay? Thursday, I'm going all day long. I've got meetings in Tuscaloosa that they assigned me the day. I said where I wanted to go, and they assigned me the day. So I'll be off campus all day. Now, when I say all day, I probably will come back because Tuscaloosa is on the way. If I'm back here before, 6 o'clock, I'll come on campus. But that's not going to be very much time. But my guess, the meeting is probably going to go until fairly late, and then it's another hour. So we'll see. I may get back for the last part of the day there. Okay? And then Friday, this is bizarre. I have a doctor's appointment that Friday, dermatology, but that's in the afternoon. Hopefully it's late enough in the afternoon I won't have to leave early. So I will be on campus probably 8 till near 12 anyway. So weird week next week, but missing this Friday, but hopefully we'll be back there next Friday. All right, any questions on anything we've done so far? Okay, we're in Chapter 12, Vector Value Functions, 12.3, Velocity and Acceleration, and we had just done the definitions for velocity and acceleration, the top of page 837. We are now on the lines just below that. For motion along a space curve, okay, not just in 1 or 2 or 3 dimensional space, but along the space curve, the definitions are fairly similar. Before this, we were talking about linear motion or curvilinear motion. But now in a space curve, if you have your r of t, which is x of ti plus y of tj plus z of tk, your velocity is just merely going to be the first derivative of that displacement vector, okay? And that would be x prime of ti plus y prime of tj plus z prime of tk, okay? Acceleration, first derivative of the velocity function, which is the second derivative of the displacement function, which is x double prime of ti y double plus y double prime of tj plus z double prime of tk. And speed is the magnitude of the velocity, which is the magnitude of r prime, which is the square root of x prime squared plus y prime squared plus z prime squared. Okay. Very analogous to what it was on plane curves. Okay. I think example 1 is sneaking up on us here. Here we go. Any questions so far? Okay. Goodness, it's cold in here. Didn't realize it was. Was the window open when y'all came in, or? Okay. I did not notice it this chilly this morning. Is the temperature dropping outside? Okay, that may be it. Because I think it started today in the 50s, and I believe it's going to not get much past 40s now. Okay, whatever. So, in example 1, find first the velocity vector, then the speed, then the acceleration vector for the particle that moves along the plane curve C, described by this. This is the plane curve, two-dimensional curve, C, and the velocity, the particle is moving along, and the t is standing for time. They didn't say that, but it has to be. So let's first do velocity vector. What is your velocity vector? V of t. What would that be? Anybody? Help me? Somebody? I'm dying up here. Freezing to death. What would it be? First is r prime of t, right? And what would that be in this case? Second derivative. You're absolutely right. And here's Fred. We're just missing Ryan. A pretty minor chain rule action here. What you get? Cosine of t over 2 I. That's yes in Navy speak. Okay, yes. Minus sine of t over 2 j. Got it. With that in mind, what is your speed? And I can't even remember what. They don't really have a symbol for speed, so we'll just do what it is. It's the magnitude of the velocity vector, which is the magnitude of the first derivative of the displacement vector, or of the curve, which is, in this case, anybody? Cosine squared t over 2 plus sine squared t over 2. And guess what that is? 1, yeah. Doesn't matter what your argument is there. It just happens to be 1. Okay? Sorry. How about your acceleration vector? This is the C part. The acceleration vector, right, is the first derivative of the velocity vector, which is the second derivative of your displacement vector, which is, going back to r prime then, that would be sine t over 2 I, it's a vector, that's 1/2 cosine t over 2j. Perfect. Okay? Now, just a little thing to note. Well, of course, there's your speed just being 1, that's how fast it's going around the thing. Whether you notice this or not, or know this or not, this happens to be describing the motion around the circle, okay? Now, since it's got sine with the I and cosine with the j, you're going to start with sine being 0 and cosine being 2, okay, or the j being 2, 0i plus 2j. So you're starting up here. And then as your sine increases and your cosine is decreasing positive, you're going in a clockwise motion around the curve. Okay, the radius of this happens to be 2, okay? You're starting there. Now it's going half as fast, is that right? As if it would be, or twice as fast. T. It doesn't really matter. But your speed vector, your velocity vector, is going to be basically magnitude 1. That's what the speed is 1. Okay? But remember your radius is 2, so you're going just a fraction of the way around per second. But then your acceleration is a vector that is going always in opposite direction of your displacement. So if your displacement is going this way, the acceleration is going in the opposite direction. But at a quarter of the rate, you might say. So I don't know if any of that is useful or helpful, but in some problems it's helpful just to sort of take a look at what's going on. And I think that's what they're going to do. So I was trying to wave my arms with it. They're going to show you, so I shouldn't have been waving my arms. Any questions on this? Can I delete? Okay. Okay, just like we did, the velocity vector is first derivative of your displacement vector, which is, just as we said, cosine t over 2i plus minus sine t over 2j. Your speed vector would then be 1, which, not vector, speed would be 1, the magnitude of velocity vector. Your acceleration vector, which is second derivative of your displacement vector, would then be this, okay? Now, what that is saying, as you see the graph coming up, oh, you don't see the graph coming up, boo-hiss. Okay, it's in your book, okay? So I'll hold it up so if you don't have a book, you can see what I was sort of rambling on about. Oh, man. Okay, here's your curve that you're traveling, your displacement vector. Circle of radius 2 going clockwise. That's what we were describing. Now, what I didn't do was pause and point out to you what your velocity vector was, but it's always, of course, tangent to that curve in the direction of travel, so it was, for instance, at that point, was pointing in that direction, tangent to the curve. Now, at that point, your displacement is from here to there with a magnitude of 2. Your acceleration is there to here with a magnitude of 1/2. Okay, our book is falling, but it's pointing toward the center of the circle. Now, what that is talking about is centripetal acceleration. Okay, anytime you're traveling with a constant speed around a circular path, your acceleration has got to be center-seeking, centripetal. You're going toward the center of the circle. And that's what I was sort of rambling about, but this picture shows it better than my ramble. Okay. So there's example 1. Any questions? Now, they're skipping example 2, 3, and 4. So let's go back and we'll do example 2 if we've got room here on this page. Okay. Example 2, sketch the path of an object moving along the plane curve given by r of t is equal to t squared minus 4 I plus tj. Okay, that's a pretty ugly j. Okay, plus tj. Okay. And it says find the velocity and acceleration vectors when t is both 0 and 2. All right, so we're going to draw our axes here. Okay, I'll just tick off a few points. 1, 2, 3, 4, 5, 6, 7, 8. Negative 1, 2, 3, 4, 5, 6, 7, 8. Positive 1, 2, 3, 4, 5. Negative 1, 2, 3, 4. Okay. It didn't put any limits on t. It just later will look for it 2 specific values. So let's just start. Why not? T equals 0. What would be your displacement vector at t equals 0? Pretty easy. Help me, somebody. T is equal to 0. Negative 4i, period, okay, plus 0j. So there you are. Negative 4 in the I direction, 0 in the j direction, okay? Give me another t. Second? 2. We jumped up to 2. When t is 2, what is your displacement vector? 0i plus 2j. So there you are at t equals 2. This is t equals 0. This is t equal 2. Okay. You chose the ones I had in the book, didn't you? Okay. Now, it says sketch the path. We need a little bit more to sketch the path. Give me something. T equal 1. What do you get? Negative 3i. Yeah, plus j, 1j. Okay, got that. So we got t equals 0, 1, and 2. Let's go for what? Second? Oh, that's not. Okay, it's too messy. Let's use a few more integers first. Negative 1, what would that be? Now, here is where things sort of start falling apart just a tad. If this is indeed the path of an object moving along there, usually you don't talk about negative times. But we will, just to get the sketch. What would that be then? minus j. So it would just be down here then, okay? Give me another t. 3, okay. What we got give you? 5i plus 3j. That would be somewhere about like that. Give me another one. 4, yeah, we did skip that. Yeah, okay. What would that give you? Plus 4j. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Somewhere out there would be 12i and 4j, maybe there, or somewhere there about it. I may not have gone high enough. Okay, somewhere out there. Let's do a few more negatives, since they did them in the book. Negative 2 would give you 0i minus 2j. There we are. Now, you see sort of something showing up here? It's pretty much symmetric across the x-axis. So let's just take that symmetry and run with it, okay? And this would be, if you had negative times, if that's what your t was representing, then you would be coming along here like this and moving along like that, and now you're in the positive time. It is a parabola, a sleeping parabola, but that is the path, okay? Now, sketch the path of the object. We did. And find the velocity and acceleration vectors when t is equal to 0. So we need a velocity vector. What would that be? V of t is going to be r prime of t, which is 2t I plus j. Okay. Let's go on and do the acceleration vector, which would be second derivative of the displacement vector, which would be 2i. Okay. Plus 0. All right. So, oh, my curve really is ugly, isn't it? I'm not hitting the points very well, I mean. So let's evaluate both of these at t equals 0 and at t equal 2. So v of 0 would be what? J. Just j. Because the x component goes away. So that is 1 unit up. At t equals 0, that's our position, and there would be the velocity vector, v at 0. Okay? What you want to do next? I'll do acceleration vector at 0, or the velocity vector at 2. I really don't care.
Velocity vector at 2 is,
okay. V of 2. 4i plus j. Okay. So here we are at t equal 2. 4i would be 1, 2, 3, 4, and 1 up. So it would just about be something like that. That's a pretty ugly vector. But it's tangent to the curve. You know it's got to be, as this one was there if it had touched. Okay? Now let's go back and do our acceleration vectors at those two locations. A at 0 would be no, 2i. It's a vector. That would be in this direction. Maybe I should be putting them in different colors. Would that be helpful? Okay. What color do you want the acceleration vector? Red. Okay. So that one would be that way. Okay? The other is velocity. How about when t is equal to 2? That's still 2I. So the acceleration vector would still be, oh, I meant to do red again. Okay. If I could draw, it would still be 2 units in that direction. In fact, that's a constant acceleration. When the object was coming this way, it was decelerating by that amount. Still decelerating, still decelerating, still decelerating. Made the turn here, and now there is, later we'll call it an osculating circle here. That would be pointing this way. And then from here on, it's still now accelerating as it goes in that direction. At the same rate, it was decelerating here. Always 2I. So we could draw in, at every point, the acceleration vector is 2I in that direction. The velocities would take a little more work, but they're doable. Okay. Oh, perfect attendance today. We made it through the cold, blowing winds, huh? All right. Now, any questions on that? They talk about this being the vertex of the parabola. So as it's coming in, and they're using as an analogy, put the sun at the origin, and this could be similar to a comet's path coming in. I kind of don't think that's right, because the acceleration to the comet would always be toward the sun, not like that. So and they do say this type of motion is not characteristic of comets that travel in parabolic paths through our solar system. For such comets, the acceleration vector always points to the origin, which is the sun. Okay. So I don't know why they even brought that up if it's not true. I'm sorry. Not this one, okay? But if you had a comet's path, those accelerations always are pointing toward the sun. And I would say they would be more realistic, because pointing this way, they're actually moving faster as they come in, this way even faster, Here you reach a tipping point and it doesn't increase, it actually starts decreasing a little bit as it makes this turn here, and then from here on, when it's pointing toward the sun, it's slowing down. And that is indeed indicative of comet paths. They're fastest when they are closest to the sun. But I don't think comets really follow in parabolic paths. They follow in elliptical paths, or at least that's my understanding. So I think that whole analogy was a little faulty. But this is a math book, not a physics or astronomy book. All right, any questions on that? Oh, let's see how they do it. Okay? And they may have even drawn a picture that could be as good as mine. Okay? The velocity vector is the first derivative of the displacement vector, which is exactly what you showed it to be. This is example 2 at the top of page 838. Oh, I'm sorry. You're right. That's right. This is back going what we did before. Wait. we still got to move back and do example 3. Okay. Let me get out of red then, back to dark. All right. Example 3. This one, you can go to larsoncalculus.com for an interactive version of this type of example. Okay? And this is sketch the path of an object moving along a space curve. These are always so much fun. C given by, here's the space curve, r of t, displacement vector as a function of time, is ti plus t cubed j plus 3tk. And this is good for all t's greater than or equal to 0. Okay? Okay. Now this is more realistically a velocity acceleration problem because you only got positive times here. Okay? The other was okay, but and then it says find, as you sketch the path of the object, then we're going to try to find the velocity and acceleration vectors when t is equal to 1. So we'll come back and do that. Now, ask you to look at how weirdly they chose their orientation of their axes, okay? Certainly they obviously knew what that was going to look like before they chose their axes, or they played around with it. Something I never would have guessed to orient them that way. So I'm going to do the way I can draw them, which isn't very good, but that's going to be x in this direction, y in this direction, and z in this direction. Okay? Now, I'll tick off a few points. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. Okay, that may not get us far enough, but let's see what happens. Have a feeling we're going to go out the possibilities of J's really quickly, because in the y direction. All right. T greater than or equal to 0. Let's start at t equals 0. What's your position? T equals 0? Yeah, 0, 0, 0. There you are at the origin. Okay. All right. There's something I'm already not liking about this problem, but we'll go ahead. Give me another t.
1.
Okay, where would you be? 1 for x, 1j, and 1k. So you're going to be right about here. Now, that's not at all clear where you are there, because that could be somewhere behind or anywhere, but you're positive x, positive y, and you just go over 1 unit from here, and then up a unit. I actually went up too far. It should be further down. This orientation is not going to give us a real good descriptor. Okay, but go ahead. Give me another. R of 0 is a 0 vector. Okay. R of 1 would be 1, 1. Wait a minute. R of 1, that would be 3 on Z. Oh, I'm sorry. I thought someone said 1. I was just following what you said. So this isn't correct. Okay? So 1 on X, 1 on Y, and 1, 2, something around here, 3 on Z. So you've gone from here to there, kinda. Okay? How about 2? R of 2. Where would you be then? 8J, 6K. Okay. 2I, 8. 1, 2, 3, 4, 5, 6, 7, 8, and 6K. 1, 2, 3, 4, 5, 6. Maybe somewhere there. Goodness, this is why the orientation really stinks, the one that I have. It just, you can't tell what's going on at all. Okay? Now, let's move on to what they're really asking for. Okay? And you see, this is what I'm having problems with. Their rendition in the book has them coming from here and going through here and coming out there. Not accurate, because they said t greater than or equal to 0. You're starting here and going around here. This end of the path is not there. That's why I was having trouble with it. Now, it doesn't help my picture any, but it does show a little flaw with theirs. Okay? Now, we've sort of drawn the picture, though it's really a lousy orientation of the thing. You have to really twist things around to get a decent picture of that. So let's do the next, which is find velocity and acceleration vectors when t is equal to 1. What is your velocity vector? V of t I plus 3t squared j plus 3k, and your acceleration vector is what? 6tj. Okay, because your i's and your j component, I and your k components go to 0. Okay. Now,
the first one is acceleration, the other one is what?
what's that?
You have acceleration and what?
It's the first derivative of the velocity vector. Did you get the velocity vector? It's the first derivative of this. Derivative of t is 1i plus 3t squared j plus 3k. And when you take the second derivative of r, or first derivative of velocity, this goes to 0, this is 6t, and that is 0 again there. So your acceleration is only in the j direction, which from what we were looking at before, it is pretty much fairly obvious there, I think. Okay. I didn't go nearly far enough, but you're really taking off and going in that direction. Okay. So your acceleration is strictly in the y direction. Your velocity vector, when t is equal to 1, what would it be?
I plus 3j plus 3k.
I plus 3j plus 3k. Perfect. Okay? So at t equal 1, you got some velocity in this direction, just a little bit, 3j and 3k. So you're going something like that, and that actually looks like it could be tangent to my curve. Surprise, surprise. Okay. And then the acceleration vector is just what? 6j. And that would be, at this point, really pulling you along that way. Okay. Now, just a couple of little issues here. I guess they're fairly good. Your velocity vectors up here has a component in the x direction, which you can see here, in the y direction, and in the z direction as well. But the acceleration vector is just parallel to the y-axis, so it's just going in that direction. At t is equal to 1, but that's going to be true everywhere. It will be only in the j direction. But the larger the time is, the larger that acceleration is in that j direction. Okay. My picture really stinks, mostly because of the orientation, but it's a pretty bad one anyway. Now, I think we've still got to do example 4. Any questions on 3?
What were they looking for?
I'm sorry?
I'm confused what they were looking
I can't hear.
for. What were they looking for?
Well, they wanted a sketch of the curve. That was the first thing. Then they wanted your velocity and acceleration vectors when t is equal to 1. And okay, I plugged in t is equal to 1 here. There was your position vector. I plugged in t is equal to 1 here. And that's your velocity vector is also 1, 3, 3. Okay, is 3, 1, 3, 3. Your acceleration vector is 0, 6, 0. Okay, so you have a pretty hefty acceleration vector in the direction of the y-axis, parallel to that. And the velocity vector, is what it is. And it is tangent to the curve, wherever that curve is. All right. Ready for example 4? Okay. An object starts from rest. Whether you're a physics student or not, but certainly the physics student should tell me what that means. Starts from rest. What does that mean?
Condition.
Say again?
Condition.
I can't hear.
It means condition, but I mean it's not moving.
It's not moving. So what would be?
Acceleration? 0?
I don't think you can tell that. But there is something you can tell. Not acceleration, but
Speed?
say again? Speed for sure. Also, velocity is 0. If you're starting from rest, your initial velocity is 0. It won't always be 0, but your initial velocity is 0. You can't say anything about the acceleration. It may be speeding up, slowing down. For instance, if I were holding, say, this eraser up here and going to drop it, the acceleration is downward, okay? So even though it's at rest here, but its speed is definitely 0 here, okay? Now, as I release it, it's going to pick up speed as it goes, okay? Same thing with just about anything. If its initial velocity is 0, well, if it's released from rest, okay? Object starts from rest at a point 1, 2, 0 and moves with an acceleration of this. So an object, I'm going to abbreviate like crazy. An object starts from rest now, parenthetical, v of 0 is equal to 0. That's what starts from rest means. Initial velocity is 0. The 0 vector, in fact, not in any dimension is it moving. Okay? At the point and this is a point here, 1, 2, 0. Okay? That's where it is at time t equals 0. So we can say from this, I was using parentheses, but I'll do it again. So r of 0 is equal to 1, 2, 0. That was the point. This is your displacement vector. Okay? And moves with an acceleration of, so your acceleration vector at any time t is j plus 2k. Okay. One thing to note there, wait. Yeah. Okay. The way they read it, that is your constant acceleration. Not a variable. That doesn't mean just at the release point is at the acceleration. This is your acceleration all time t, and that's why I put the t in there. But notice there's no time dependence here, so this is a constant. Okay? Your acceleration is a constant vector. Okay. Now, where a of t is measured in feet per second per second. Now, I don't know why they threw that in there, except just to tell you what unit it was going to be. It says find the location at t equal 2 seconds. Find r of 2. I'm going to really abbreviate there. R of 2, that's what we're looking for. Okay? Now, what would be your approach? Absolutely. That's the only vector you've got to go from, so we'll integrate that. Okay? And what will that give us? That will give you a velocity vector. V of t is equal to the integral of j plus 2k dt. Right? Now, they leave that as a indefinite integral because we don't have an interval to go on, just an indefinite integral. What would that be? Tj plus 2tk plus c, but that c is a vector. Okay? Now, you know that your v of 0 is equal to 0. Remember, we wrote that down. So that means when your v of 0 is going to be what? 0 vector, and that is going to be 0j plus 0k plus c. Well, I guess we just proved that our initial velocity is 0 because that's what it is. That wasn't very instructive, but that's just 0. Okay? What are we going to do with that then? So this now is 0. Don't even mess with that. Next step, integrate that to give us our r of t. And that would be integral of tj plus back off just a second here. If you have a 0 I, yeah, you're still going to be, I was going to say you could have a constant I component, but if you did, that's still going to be 0 because it's a 0 vector there. So I think we're okay. Plus 2tk dt. What would that give you? T squared over 2j, right? T squared k is equal plus some other, we'll call it c since we didn't use the other c. Now, we know that when t is equal to 0, r of 0 is going to be 1, 2, 0. Okay? And when we plug in here, that will give us what? That's going, yeah. The j is going to be 0, k is going to be 0, so your c vector is going to be that vector right there, 1, 2, 0. Okay? So let's go back and do what you're, see, where are we? What are they asking for?
T equals 2 seconds.
Yeah.
T equals 2.
Find the location. That's looking for r. So what we're looking for now is, let me write what r of t is then. Based on what we just did, r of t then is going to be I, that's from here, from your C, plus t squared over 2 plus 2 j plus t squared k. Okay, that is your displacement vector because it's this thing here. There's your j component, k component, and c will contain your ij and k here too. So we include the 1 for the I. We include t squared over 2 plus 2 for the j and t squared for the k because it's added component with 0. So this is r of t at any time t. And what we're asking for, what is it at time t equal to? So r of 2 would be equal to what? I plus 4j, because 4 squared over 2 would be 2 plus 2 is 4j plus 4k. Okay, that's what we get it to be, and sure enough, that's what they got to. I plus 4j plus 4k, when t is equal to 2. Okay.
How do you
Yeah.
vector C?
I'm sorry?
Vector C in the beginning?
Vector C?
Yeah, very beginning.
Okay, we had 2 of them. The first one, because your initial velocity was 0, this had to be 0, so C has to be 0 too. Because this would be 0, 0, C would have to be 0. If that was anything other than 0, you'd have a velocity t equals 0, not 0. So that can be threw away. This one, however, when we put our initial condition in, r of 0 is equal to 1, 2, 0, that means your guess it's right here, r of 0 is equal to 1, 2, 0. And because r at 0 would make this 0 and that 0, then the c is going to be everything that's left here. And that's 1, 2, 0. Is that what you're asking? All right.
Yeah, that part is amazing.
Okay. What you did, you plugged in t equals 0 here, here, and you knew that had to be this. And you get a plus c. So these two were just 0, so that left your c. So c is that. A 0 component on k, but a definite component on that. And then when you put that in its place, c up there, that would be 1 from here, I, plus t squared over 2j plus 2, t squared over 2 plus 2j plus just t squared. Okay. Because you see, when you plug in a 0 there, these two go away and you just get c is equal to 1, 2, 0. Just when you plug t equals 0 in that part over there.
You know what? That's amazing.
Okay? Making sense? Okay. Everybody got it? Did you have a question too?
Right here.
Okay. Boy, that's what a surprise. Okay. All right. Now we're moving to, if y'all got this, everybody got it? Okay. Projectile motion. Okay. You now have the machinery, the tools in your belt to derive the parametric equations for the path of a projectile. Now here's some assumptions. We're assuming that gravity is the only, sort of hate the way they phrase this. This is not a physics, okay? It says assume that gravity is the only force acting on the projectile. If you're going to say it that way, say the force due to gravity is the only force acting on it. If you're saying just gravity the other way, weight is the only force acting on it. You got to, gravity, when I see or think gravity, I think acceleration due to gravity. Not a force, but an acceleration. But this is a math person, okay? It's the only force acting on the projectile after it is launched. Certainly when it's launched, you exerted a force on it, but as soon as it left the catapult, your arm, whatever it was that shot it into space, as soon as it left, the only thing acting on it is gravity trying to pull it down to Earth. The acceleration due to gravity, pulling it down toward Earth, okay? So the motion occurs in a vertical plane, which can be represented by the XY coordinate plane. This is your displacement in your initial direction that you fired the thing, or threw the thing, or whatever, and this is your vertical, okay? One is a lateral displacement, one's vertical displacement, okay? Just have that so that your initial velocity is in that plane. With the origin as a point on the Earth's surface, be fine. Then this would represent initial height, that would represent initial velocity, and your only component of acceleration is downward, and that's the acceleration due to gravity. Not a force, but an acceleration due to gravity. Okay. Even right when you fire it, acceleration due to gravity. Somewhere at the maximum point, acceleration due to gravity. Everywhere along the way here, the only force downward, the only pulling downward is your acceleration due to gravity.
What's the difference between force, weight, and acceleration in application to gravity?
Okay. Force and weight are the equivalent. Okay. Acceleration. You have had physics yet? Or you have?
We're in there. I just don't know.
Okay. Acceleration is change of velocity. So it's meters per second, or meters per second squared. It's always an acceleration. A force is a mass times an acceleration. Okay? So that's why weight would be a force. The force due to gravity, that is weight, that would be a force. Okay? Or any other thing that you had pulling it down. If you had it on a bungee cord, then that would be a force pulling it down. Okay? Or pulling in whatever direction that would be. So this is projectile motion where the only force acting on it after it leaves is whatever projected it is the weight pulling down. Acceleration due to gravity. Okay. That's top of page 840. Okay? For a projectile of mass m, the force due to gravity is F is equal to minus mgj because it's in the y component. Okay? And it's minus because it's always pulling downward. So that is your force due to gravity. There they said it correctly. For the acceleration due to gravity is either 32 feet per second squared or 9.8 meters per second squared, depending on what unit your measurements are in. Let me just give you a hint. If you're dealing with mass, the odds are you're in SI units. I hope some of you know this now. What is the unit of mass in the U.S. customary system? Second? No, that's a force. Slug. No one ever uses slugs, okay? So if you're using this, the odds are you're using SI units. By Newton's second law of motion, the same force produces an acceleration, A is equal to A of t, and satisfies the equation F is equal to ma. Okay? This is the weight of the object, force due to gravity. This is your motion, mass times acceleration, whatever your acceleration is. But what they've just told you is the only acceleration you have is the acceleration due to gravity, so you can just plug that in. And that's what they did here. Consequently, the acceleration of the projectile is given by ma. Now this is not the acceleration. This is the force of the acting on the projectile. The net force on the projectile is given by ma. If it's acceleration, it would just be a. ma would be the net force acting on it, is equal to minus mgj. Because that's the only acceleration you have on it, that's the only force you have on it, is downward. Acceleration due to gravity. Which implies a is equal to negative gj. They said that at the very beginning. They're finally getting around to saying it here. Okay? Here's example 5. A projectile of mass m is launched from an initial position r0 with an initial velocity v0. Find its position vector as a function of time. Okay? No numbers in this one. We'll introduce a few maybe on the way, but what is your acceleration here? They just told us a little earlier. What's that again?
The velocity is 0.
Okay, we don't know it's 0. It's v0. That doesn't mean 0. Okay? The acceleration is what? Minus gj. Minus gj. That's it. That's the only acceleration you have. Acceleration due to gravity pointing toward the center of the earth, which is in the minus j direction. Okay? Now, what would we do with that? Not take a derivative, integrate it. Okay? And since minus g is a constant, we'll just integrate that. So this will be And the integral of this is, the integral of that is v of t. Okay? So, what is the integral of that? Minus g, oh, I left off my dt, sorry about that. Minus gt plus some constant c. Some vector constant c. I left off my j. Goodness gracious. Okay, I'm leaving off lots of things here. Huh?
I didn't know where the J was going to go.
Don't know what?
I didn't know where J was going to go.
No, it goes down there, yeah. Okay. Minus g, j. I don't like it there. Let me put it inside, outside. GTJ. Okay. That's your component in that direction. Plus C. Now, this is V of T. Let's plug in V of 0. And what will that be? That's your V0. So, and that's equal, because when T is equal to 0, that's 0. This is now your C. So rather than C, we can put V0. So now our velocity vector, V of T, for all times T, is equal to minus GT J plus V0, whatever that initial velocity is. Okay? And then what are we going to do with that? Integrate it again, and that will give you R of T. And if you integrate this, dt. And what will that give you? Minus g t squared over 2 j plus v0 t. Okay? Yeah, you got to have a t. So you're integrating dt. This is a constant that gives you v0 t. Now this is a full-fledged, could be a full-fledged velocity, you know, with x, y, and z components. And you'll take the y component and add to this one. But the x and z, they're there. Okay? Wait. You don't have a c. This is two-dimensional. Okay, two-dimensional. So it's just x and y components. Okay. Sorry.
C was a vector, right?
C was a vector, and that happened to wind up being your initial velocity vector. Now, yeah, this integral, you got to put another C. Now, do you mind if I use C again, or you want me to use C1 or K or?
C. Just C1.
Just C, okay, C1, okay. Now, but we know that R of 0 is equal to R0, right? I don't know if that is a 0 and O. I don't know which. It looks sort of like a 0, so I'll make it a 0. It could be O for original displacement. But all these are, this T and that T are both 0, so this is your C1. So we don't need to write C1 anymore. We'll have this. So what is your R of T? It's minus 1/2 GT squared J plus V0, a vector, T, plus R0, another vector. So I'll make those zeros, not O's. Okay? That's it. Okay? So if there weren't many numbers in it, the 1/2 showed up. So That's the only, and the 2. Those are the only numbers you see, understood 1s in other places. So that's your basic formula. That's your displacement for vertical motion. Okay. Now remember, this is 2-dimensional motion, so this only has an x and a y, an I and a j, and that only has an I and a j. Okay. It could have been 3-dimensional motion, but they didn't. Usually vertical then would be the z. Okay. Got it? We still have a question.
Just change the format. Instead of negative g t squared, which you put 1/2 g.
Oh yeah, I just moved it.
Yeah, is that the formula they want you to
This is the one you'll see most of the time.
Okay.
So that's why I changed it to that form. This is very standard. If you're dealing with scalar functions, you just leave off the vector notation, and this would be exactly it. Leave off the j here, the vector notation there, the vector notation there. That's what it would look like. Okay. And that would be your position at any time t. Okay, and that's what they got. Well, let's see. Let me clear the space here. Now, the only thing, they put the t in front of the v naught. I guess they put the vectors at the end. But here's how they do it. It's very similar to what we did. Begin with the acceleration as a function of time. Y is your minus g j. That's the only acceleration you have, and it's a constant. It's not got a time dependence on it. Integrate twice, okay? The first time you integrate gives you the velocity vector. Now, I don't know if this is helpful or not. To me it is. And I should have done it this way the first time. A of t is equal to minus gj, okay? And this is dv dt, okay? And then, now pure mathematicians probably hate for me to say it like this. Write this in differential form and put your dt over here, and then integrate that, okay? And that gives you, integrate this, and this gives you v of t, and this is equal to minus g t j plus C1, they call it. And they make it a capital C, I don't know why. But anyway, that's exactly what they got there. And if that's helpful to you, write the A as dv dt, and then write that in differential form with the dt over there, and then integrate both. Integrating a perfect derivative here gives you v, integrating this gives you that. And then your constant of integration turns out being your initial velocity, okay? Because then you plug in, they're going to wait till the end to plug in, which I think is a little ridiculous, but it's fine. And then how you get this equation is by rewriting this as dr dt, and then you do your dt here, not there, and integrate this, and this gives you r of t, okay? That's sort of what they do, and does that, and so now you get your C1, T, and then your C2, and that's basically what we did. And I still haven't figured out why they capitalize the C's. They're just constants. To me, a capital C in this context would be a curve. But these aren't curves, these are vectors, okay? So I wish they'd use littles, okay? Now, what they're going to do, you can use the initial condition that V of 0 is V0 and R of 0 is R0, and you solve those for the constants vectors C1 and C2, and you get C1 is V0, C2 is R0. So why in the world do they capitalize? I don't know. And that's the same thing we did. So the position vector is R of t is minus 1/2 gt squared times j. That is the only one that has a real component here, plus tv0. Now that has a component in the x direction and in the y direction. This v0 is a two-dimensional vector, okay? And then your r0, that could have two dimensions as well, okay? x0 and a y0. But, say again?
I just had a question. Whenever there is a constant vector, is that always going to be is that always going to be just explained as velocity and acceleration? Or is it just for this question?
Okay. If what you're asking is if your initial velocity is a vector, that will be the constant that is there. And if your initial position is a vector, that's the constant that's there. It could be those are this one could be 0. You know, you're on the ground to begin with. You're not up in the air or down in a hole or anywhere else. But that would be your initial position, wherever you have to be. If you're up on a mountaintop, that would be your R0, okay? And if you fired it at an angle of 45 degrees, it would be there. 5 degrees would be there. That determines what your V0 is.
But that's a constant regardless.
Yeah. Your initial velocity is a constant. Your initial position is a constant. Yeah. All right. So that gives us the formula that hopefully we were expecting anyway. And if you've had physics, hopefully you've seen that before. Okay. Most of the time we don't deal with the vector equations. We deal with x, y's, and z's. Okay. Or y's. In many projectile problems, let me make sure that I'm not skipping anything. Yeah. In many projectile problems, the constants, vectors, R0 and V0 are not given explicitly, if that's what you were asking. Often you're giving initial height, that's what I was trying to say. If it's given as a vector, that's it. Oftentimes it's just given as a height, okay? If that's the case, then that's going to be hj, okay? You don't have a horizontal component there, just a thing. And you just assume your x0 is 0 here. Your y0 would be h. And the initial speed is bold V0 would be velocity. Italicized V0, that's speed. Okay, I don't write bold, I don't write italic, so you just have to pick it up from the context. Now, initial speed V0 with an angle theta at which that projectile is launched. If that's what they give you, then what you do is you break that initial velocity into, and you know its angle, okay, because the angle at which it's launched, that's the angle of the initial velocity. So break that into an x component and a y component. And that you get from trig, right? X, the cosine of theta is x over V0. Now, okay, this V0. I can't tell looking at that which one this is, because they look like they bolded it, but if so, yeah. But this would be the speed, which is the magnitude of this thing, okay? So this distance x, so the cosine of theta is x over V0, and the sine of theta is y over V0, this V0, okay? So there you have your components of your, that V0, the vector V0. Cosine, this V0 cosine theta, this V0 sine theta, okay? And that's what they're showing here, okay? This V0 is magnitude of that V0, or this one, and this V0, same thing. So x is V0 cosine theta, y is V0 sine theta. Yeah, the magnitude of V0 sine theta. Okay. That's more realistic. Now your initial height is all in the j direction. Usually positive, okay, if you're up on a hill or something like that. And your initial velocity, even though they could, if they gave it to you in XY components, you already got it, okay? If they just give you, I mean, if they give it to you as a vector, that's in X and IJ components, okay? If they don't give it to you as a vector, but give you just the speed, then you break that down this way. Speed here, X is speed, cosine theta, Y is speed, sine theta. Okay. Now, from the given height, you can deduce that R0 is just Hj, a positive Hj. That's what I was saying before. Because the speed gives the magnitude of the initial velocity, it follows that this V0 speed is magnitude of bold V0 vector, okay? And then this V0, bold V0 is xi plus yj, where the x is this V0 cosine theta, and the y is this V0 sine theta, okay, ij. And that would give you your x and y components, the x component and y component of your initial velocity, depending on what angle you're doing. A shallow angle is going to have a large horizontal component of the velocity, very small vertical component of velocity. Steep angle, small horizontal component of velocity, a large vertical component of velocity. That's taken care of by your angle. V0 is that magnitude, your hypotenuse. Okay. So now the position vector can be written in this form. Remember, that was our original. Okay. Now we've got this. The minus g t squared j, that's fine. The plus t times v0, that's your initial speed, times cosine theta, I, plus t times the initial speed times sine theta j, plus hj. Okay, look at what we've got. I component, 1, right there. V0 cosine theta t I. That's it. Your j component, you have an h constant, you have a V0 sine theta t. And why in the world they put the t's in front here and behind there, I don't know. Okay, and then your j component in this is 1/2 gt squared there. A minus there, plus here, assuming you're firing it upward. Okay, which is where we usually do. All right. What does this tell us? One thing, the horizontal component, the horizontal displacement is a function of time. Okay, linear function of time. Whatever that initial component was here, however long it's in the air, that's that. It's not reduced, it's not increased, it's a function of that time. Okay? A linear dependence on time. Whereas your vertical, that gives you your parabolic shape. Some initial position, some, your initial speed is up this way, reduced by your acceleration in that direction. So this gives you the j component. If h was positive, you started up here, and then if this was an upward angle, you're boosting it this way, but acceleration due to gravity is pulling it down. Okay. All right. So this gives us theorem 12.3, top of page 841. Neglecting air resistance, which is something we've been doing here because we said the only force acting on the object is its weight. Okay? The path of the projectile launched from an initial height h with an initial speed, not velocity, speed, v0, an angle of elevation, theta, and they said elevation, so we're assuming it's not a depression, elevation is described by this formula, R of t, your only component in the horizontal direction is your initial velocity in that direction, times however long is going in that direction. But your vertical component, you have an initial position upward, an initial velocity upward that's multiplied by time, and then the acceleration downward that is multiplied by time squared, 1/2 g t squared. Those are your j components, where g is the acceleration due to gravity. Now, since this formula doesn't have mass anywhere in it, okay, then all you have to do, you can use your U.S. customary. If R is given in feet, then that's fine. Use 32 feet per second squared. Be sure your initial velocity is in feet per second, okay? And this is in feet, okay? Of course, feet per second. What's that?
Is it possible for you to calculate projectile motion or position with it being three dimensions?
Yeah. The only, that's why I sort of hesitated before. In 3 dimensions, usually it's your k that's vertical, okay? And your x's and y's are horizontal, but you have one component here and one component here. So those, then your i's and j's will look a lot like this, but then here's where you have a problem. How are you measuring that angle theta, okay? Yeah, you would have to have an angle, an azimuth angle as well as an altitude angle. And that gets messy. It's doable, very doable, but then this would be your k component. And again, this component here would have both an x and a y. And it's doable, but I don't want to do it. Now, you would almost need spherical coordinates to do it well. Okay. So let's start with a baseball is hit 3 feet above the ground. That's a good swing right about waist. Okay, caught it really good. At 100 feet per second. That's its initial velocity. Okay, by the way, this would be its, yeah, the h that we used before, which is initial displacement. This would be speed. Okay, 100 feet per second would be its speed.
Oh,
at an angle of 45 degrees, those two things together give you a velocity. Okay, so 45 degrees with respect to the ground, as shown in this figure, and it says find the maximum height reached by the baseball. Okay. And we also have, will it clear a 10-foot high fence 300 feet from home plate? Okay. Looks a bit closer than that, but we'll take their word for it. Okay. All right. Now, you want to start with your formula? Okay. This was what we said was your h. This was your v0, not vector v0, but v0 speed. And this was your theta.
And that g is...
What's that?
G is 32 feet per second squared.
Yes, and if you're doing this, then the other thing to note is that your g that you would use here would be 32 feet per second squared, or feet per second per second. You're absolutely right, because you're using feet everywhere else. Okay, so we'd use that.
So now we can use our formula.
Yep. What is that formula? R of t is equal to
the speed times cosine theta.
okay, 3, is that what you said?
Yeah.
Yeah, okay, my hearing's bad. 3 cosine 45. Can I go on and put that in?
Sorry.
Huh?
It should be 100. that's.
Oh, yeah, I'm sorry, yeah, okay. Oh, you said V. I thought you said 3, and I thought that doesn't sound right. Okay, good. You want to put down the formula first. Let's do that. That would probably be a wise move. V0 cosine theta t I okay. Probably I should have put that inside there. Okay. So I feel like I need another one in there too, but it's okay. All right. Plus, what goes here? H plus V0 sine theta t. That just looks so awkward to me. I'm going to put them in that, okay? Say that again. Yeah. Minus 1/2 GT squared J. Got it. Okay. All right. Now, there's your formula. But what are we looking for? The maximum height. What is that going to be? Okay. Now let's think about it in terms of what's going on here. This is your component of basically displacement as a function of time, and we don't even know the time, but that's your horizontal displacement. No vertical thing to do with it. So the maximum height is all going to depend on this J term, right? What's going to be true about that J term?
It starts with an initial of 3 feet.
Say again?
It's initially at 3 feet. It's initially at 3 feet.
Okay, that's true. But it's going up too because he's hitting at an angle of 45. But it's coming down too because of the acceleration due to gravity. So this is the J displacement, and that's going to be the height. What you might say is this is horizontal displacement as a function of time t. This is vertical displacement as a function of time t. In other words, height as a function of time t. So, what do we want to know about this? Where it reaches its maximum height. Now, first, tell me what this is going to be. This is some function of time, and what kind of function is that? It's a parabolic because of second degree, right? So, what we want to know is how high it is at its vertex. Yeah. And by the way, this is opening downward because your A here is negative, right? Okay? So we know it's opening down. We want the height right there. How do we find that? What course is this on?
You plug in,
Okay.
find out where it's increasing and decreasing.
Okay, you could do that if you were in pre-calculus algebra. But since we're in calculus, how would we get
The second derivative?
Say again?
Second derivative?
First derivative. And set it equal to
0.
0, because that's where your slope is 0. See right here, the slope is here, 45 degrees. Here it's going to be a little less, a little less. When it reaches that maximum, it's going to be the slope of 0. And then it starts going down this way. So all you do is take this thing, take its first derivative with respect to time, set it equal to 0, that's going to be the initial height. Now that may not be how the book's doing it, but that's, to me, what makes the most sense. I haven't looked to see how they're doing it, but does that not make sense okay to you? Okay, so let's plug in the number, okay? Let's do, I want to actually call this h of t, but that's probably not a fair thing to do. But is that okay to do? And that's what this is? H of t is equal to, and let's just plug in the values here, like you said, h was 3 plus 100 times the sine of 45. We know what that is. Okay. T plus, minus what's half of 32? 16. Oh boy. Okay. T squared. Okay. That's going to do it for us. Let's just figure out what this is. What is sine of 45? Y'all know that. Second? Yeah, so this will be 50 root 2, right? The over 2 part. Okay, all right. So here's what we got. Now, what we're going to do with that? Take a derivative. Okay, and what would that be? 50 root 2 minus 32t. Okay? Oh my. We got a time in there. Oh, yeah. Well, let's just set it equal to 0 and solve for t. Okay? That'll work, won't it? So t is equal to 50 root 2 over 32. Did I do that right? Yeah. I'm sorry?
If I did the derivative, I noticed that 50 square root 2 did not go anywhere.
Did not.
Because it had a t.
Yeah.
I get 2.21.
2.21 seconds. Okay? Now, if I want to know how high that's going to be, I'll plug that in my h. h of 2.21 seconds is going to be, and 3 plus 50 root 2 times 2.21 minus 16 times 2.21 squared. Oh, I thought you were punching. Or punchy. No, never mind. Okay.
You said the
We're
time.
at 81 point.
125 or something like that. Okay. Well, they said about 81 feet. Okay. All right. So don't believe that left fielder's going to be able to jump up and catch it. No. Okay. If so, he should be playing basketball. Okay. Never mind. Okay. Now, so that's the maximum height. The question is, will it clear a 10-foot high fence located 300 feet from home plate? Yeah. Okay. Now, okay. What's that? All right. So your R of t is your displacement function, right? Okay. Well, answer me this. The displacement function, when this is the horizontal displacement, that's the vertical displacement, right? Yes.
Yeah.
Okay. Now, we use this to get that one. Let's use this and set this equal to the 300 feet. So we've already, what is v times cosine of 45? It's also squared. So that's also a 50 root 2. So that's not changing there either. So we got 50 root 2 times t.
What is v
I'm sorry?
What is V zero? 100.
Yeah, that was our 100 right up here, right?
We're setting this equal to 0 now.
Say again?
We're setting that equal to 0?
No, equal to 300. Yeah, we want it to go out there. Let's see if it reaches there, okay? Divide that, that would be 6 over root 2, wouldn't it? You get that? Divide 300 by 50, you get 6, and divide by root 2, and you get 6 divided by root 2. 8.48 seconds is when it.
4.24. 6 divided by root 2?
Yeah,
I got 4.24.
that sounds better to me. Okay, did you do it? Okay, exactly half that. Okay. Say that again. 4.24. 4.24. Okay, seconds. That sounds right because this is just approximate. When it reaches its maximum height, it should be about halfway to the wherever it's heading. And this was 2.21. That's a little over halfway that. So we're not sure it's going to do it or not, but let's see. Okay. Now what we need to do is find its height at 4.24 seconds. And this is its height, isn't it? So we can go on and plug this back in here. Rather than plugging in 2.21, which is maximum height, we want to know the height when it goes 300 feet, which will be 4.24 seconds. So plug that in here. 3 plus 50 root 2 times 4.24 minus 16 times 4.24 squared.
Minus 16 times 4.24 squared.
15.17.
You get it?
So are you doing H of 4.24?
Okay. Yeah, I'm doing H at this time. What is the height when it reaches this 300 feet?
H equals 3 plus 4.24 plus, minus 16, and the time is what? 4.24?
Okay. 3 plus 50 root 2 times 4.24 minus 16 times 4.24 squared.
I got 15.17.
Okay. 15.17 feet. Let's just say around 15 feet. Oh boy, you think that left fielder can even pushing off the wall?
Can get 15 feet high in the air?
Huh?
Can get 15 feet high in the air?
15 feet high when it reaches that 300 feet. Yep, it's going to clear the wall without any chance. Well, if that guy could have jumped up on the wall, and then maybe, okay, but I don't think he had time for that. Yeah, they said about 15 feet, and that's what we got.
No.
All right. And you see, it's got little holes in it, so maybe he could get his feet through there. Okay. Y'all are getting ridiculous. Okay, never mind. All right. Let's see how they did it. Will it be anywhere like we did? You're given the H equal 3. We got that. V0 is equal to 100. We got that. Feet per second, feet and feet per second. And angle was 45, and I'll take it we must be out of time. All right. Let's just see how they did it quickly. They did all that just like we did, pretty much. Velocity vector is that. And the maximum height occurs when the vertical velocity was, the first root of that was 0, and we got t as 25 root 2 over 16, which was, yep, that's exactly what you got. And the maximum height was then, when you plug that time in, and they plugged in all those 25 root 2 over 16 rather than 2.21. Isn't that nice of them to do? Okay. And got that, which came out about 81 feet. And then they rounded off like crazy. Okay, so they kept it exact until then and then rounded. Okay, so it's 300 feet when it was hit, so that's where your X component, which is exactly what we did. When you divided that, you got 4.24 seconds, which is exactly what we got. And then at that time, the height of the ball was, and you plug that back in to your vertical displacement, and you got that, of course, which is about 15. Yep, clears a 10-foot fence for a home run. It's out of here. Okay, and so are you. Okay. Oh, and that's the end of the section as well. And that was the last thing on the slide. So homework exercises, any of the I's 3 through 9, they're all at Calc Chat. 3's at Calc View. 11 through 19, they're all at Calc Chat. 15's at Calc View. 21 to 25, all at Calc Chat. 21's at Calc View. 27 through 39, they're all at Calc Chat. None are of them at Calc View. 41 should be at Calc Chat. 43 should be at Calc Chat. 45 should be at Calc Chat. 47 or 49 should be at Calc Chat. 51 should be at Calc Chat. You can explore doing 53 or 55. They should be at Calc Chat. If they're not, I wouldn't mess with them. 57 should be at Calc Chat. 59 is a proof. If you want to do that, you certainly can. And 61 and 63 are true false. They should be at Calc Chat. We'll begin next time with 12.4, tangent, vectors, and normal vectors. We won't do any abnormal vectors next week at all. Okay. So, have a good weekend, and we'll see you Monday, and maybe see one of you tomorrow. Remember, I'm not going to be on campus Friday, and then next week I'll be in and out a lot. Have a good weekend.
Bye.
Bye-bye. Okay. Oh, maybe it would help.